Space, the final frontier, a realm of infinite possibilities and mysteries. 007 that have puzzled humanity for eons, from the vast voids that punctuate the cosmos. 012 to the very beginning of time itself. Join us on a journey as we explore the enigmas of the universe and ponder its 019 future. Will travel back to the dawn of the universe, witness its evolution, and 025 gaze into the distant future. Will seek the boundaries of the cosmos and question if there truly is an 032 edge to all we 047 know. In the vast expanse of the universe lies a deep mystery that eludes our 053 understanding, a mystery that stirs our imagination and challenges our understanding. It is the question of what 101 lies beyond the universe. As we travel through space, we're faced with the realization that 107 our vision is limited and imprisoned within the confines of our observable universe. What lies beyond these 114 boundaries remains a mystery, a cosmic curtain that envelopes the secrets of 120 existence. The very concept of beyond becomes a philosophical problem. How can 126 we comprehend the realm that lies beyond our perception? This is a challenge that pushes the boundaries of human thought. 133 sparking our curiosity and encouraging us to seek. 139 answers everything we see, from the interior of a room to the most distant. 145 galaxies that can only be seen through huge telescopes. Everything that can reflect or direct light to us is the 152 observable universe. Currently, the radius of the visible universe is 158 46.5 billion light years. However, the age of the universe is only 13.8 billion. 205 years. How to explain this discrepancy? Well, it all comes down to the expansion. 211 of the universe. As a result of this expansion, the areas from which the light 216 is emitted are moving away from us, and so we observe them at a great distance. 221 these 46.5 billion light years are the boundary of our universe. Even if the 227 entire universe is infinite, modern cosmology does not know what may lie beyond the observed 233 boundary. These cosmological limits or horizons are dictated by life itself. We 239 don't see the night sky completely filled with stars because of the limits set by light. For example, light has a 246 certain maximum distance from which it can reach observers on Earth, as if there were a spherical barrier around us. 254 beyond which there are billions of other distant stars and galaxies. This is 259 called the particle horizon and the event horizon. However, these two concepts 304 differ from each other. While the particle horizon establishes the distance from which light in the past 311 reaches us, now the event horizon is the distance from the present to an observer 316 in the future. But beyond these horizons lies another limit, the Hubble horizon. If 324 space objects are beyond this boundary, it becomes impossible to see them even after billions of years. They are 331 constantly moving away from us at the speed of light. So because of this, it 337 seems to us that the universe is limited, although in fact it is just light itself. 343 that is limited. You're well aware that the light coming to us from bright cosmic objects 350 doesn't travel at infinite speed. For example, the sun is located 94,357 miles from the Earth, in which case light will only take 8 minutes to travel from 403 it, and the star Proxima Centauri is located 4.2 light years away from the 408 Earth, in which case light would also take about 4.2 Earth years. So it turns 414 out that we can only see events that happened a certain amount of time ago in the past. Yes, we can say that we look for 22 back in time when we look up to the sky at night, so to update our knowledge. For 29 about some extremely distant objects such as the HD1 galaxy, which is located 435 13.4 billion light years away, we would need to wait the same amount of time. For 40 provided there are no obstacles like black holes in the way of light in particular. If we could examine this 447 galaxy in detail, we would learn how our galaxy was formed in the early stages of 452 the universe. Therefore, light detection is important for studying the evolution 458 of the universe, and it is thanks to this that we were able to develop the Big Bang theory. The 505 consequences of the Big Bang could not but leave a trace. Such a trace was found 510 by researchers in the 20th century who studied theories of the origin of the 515 universe. Back then, astronomers Pinus and Wilson picked up a strange signal with their radio telescopes coming from 523 everywhere, and with the same intensity. It turned out to be a remnant of the first light that appeared in the 529 universe. Cosmic microwave background radiation in 530 for the early stages of the Big Bang. Atoms could not form electrons and protons. 540 could not combine due to the extreme temperature, the radiation of photons. 545 particles of light were scattered from electrons or absorbed by them, and 551 therefore light could not travel far. The universe was then as a dense 556 fog. However, after 80,000 years, everything began to cool down. The first 604 stable atoms appeared, so the cosmos became transparent and light was able to. 609 spread freely over long distances, and it is this light with its 614 temperature above absolute zero, 454 to F, that we record as microwave radiation. 623, which can be seen in any direction from the Earth at a distance of 13.8 billion. 629 light years. It is precisely because of this distance that scientists assume. 634 that the age of the universe is the same number of years, although, as you already know, this may be only the limit of our 641 vision. Nevertheless, the SIMB cannot be seen by human eyes. The intensity of the 647 first light is too low. This is due to the expansion of the universe, which 652 we'll discuss later, which causes light waves to stretch and lose energy. So 658, they're barely visible and are in the microwave part of the spectrum. Nevertheless, despite its low 705 power, the LHC allows us to look through the crack of the beginning of the universe, as we know it, the whole image. 712 of the past is revealed to scientists. It is thanks to the LHC that we now know. 717 about the Big Bang scenario and how the world developed from singularity to this very moment, thus the map of the sky. 725, where you can see the temperature fluctuations of relic radiation, is a spotted pattern where blue areas are 732 below the average temperature and orange areas are above it. These spots allow 737 scientists to study the evolution of stars and galaxies since density changes. 743, also called seeds of structure formation, have formed the hot and cold spots of the SMR. In addition, the largest spots, 751 covering 1 angular degree in the sky, have become one of the proofs of the flat model of the universe. Smaller spots, 758, in turn have revealed a wealth of data on the composition and age of the cosmos. 80, for thus the study of the temperature features of the SMB has become another proof of the existence of dark matter. 810, and dark energy. Back in 2003, a group of astronomers led by D.N. Spill found the 817 amount of dark matter, and dark energy exceeds ordinary matter by several times. 823, according to the latest measurements, the amount of dark matter is 26.8%, dark energy is 831, 68.3%. Finally, the CMB also revealed to scientists the approximate rate of expansion of the universe, 42 miles per hour per 840 megapark. Thus the CMB provides modern science with a wide range of information. 846 about the early and present universe, and in particular helps to understand what 851 the future holds for it. It turns out that both the SMV and the space horizon 857 limit what we can see from Earth. Let's now take a closer look at what space horizons are and whether we can still 905 look beyond them. We've already mentioned that the cosmic particle horizon is an imaginary 912 line that forms a boundary for the visible universe, setting a certain distance from which light launched in 919 the past can travel to the observer, so if other cosmic objects are far from the 925 horizon, we cannot see them now. However,